So our next speaker is Sergei Stepanov. Sergei received his PhD in X-ray scattering theory from the Institute of Crystallography from the Russian Academy of Sciences. He has been at the Advanced Photon source since 1996, where he initially built control system for BioCat, and then for the National Institute of General Medical Sciences and National Cancer Institute Structural Biology Facility. There he is a section leader of control systems. His title of his talk is Beamline and Experiment Automations for the General Medical Sciences and Cancer Institute's Structural Biology Facility at the Advanced Photon Source. So please.
Thank you. Good morning, everyone. So as the chairman said, I represent here Structural Biology Facility at the Advanced Photon Source. We are commonly called GMC at APS due to our sponsors. We are sponsored by General Medicine and Cancer Institute of the National Institute of Health. We are at Sector 23, so we are a relatively small facility for this conference. But since we do all aspects of computing, not only beamline controls, but also networking, storage, remote access, and so on, so we can be viewed as like a scaled down small pony of in this business. First of all, my collaborators, these are Oleg Makarov, Mark Hilgard, King Hu, Robert Fischer, and Janet Smith, all of the GMCA. Janet is also at the University of Michigan. She is head of our project. The first three in this list are members of our control group, which consists of 4 people, including me. I would also like to acknowledge all the staff of GMCA who contribute testing and some ideas. And as I said, we are sponsored by the NIH, and Beamtime is sponsored by Department of Energy. This is a layout of our beamlines. We have 2 undulator beamlines running from a canted undulator. They have monochromator optics, mirror focusing optics, mini beam pinhole collimators. The beam actually comes to the goniometers where the crystals are mounted, and then the scattered radiation is recorded by area detectors. For a long time we were using Mars CC detector. In the last couple of years we replaced both of these Mars detectors by Pilatus 3 and Eiger 16 by Detectors, but we still have a Mars CCD detector on our beamline, bending beamline, which is not shown here. So most of work about automations I will be talking to you about will be concentrated around most efficient usage of these 2 new fast detectors. So this schematic shows you principle of X-ray macromolecular crystallography experiment. It's quite simple. In most cases, you mount a crystal on a goniometer, you rotate it. Sometimes you may also shift it left, right, down, up, down in order to search for crystal, and you record images. So this is well defined, and it allows for good automation. That's why not only our beamline, but all crystallography beamlines around the world are very well automated, because compared to other synchrotron radiation beamlines, it's much easier to do. We have more or less uniform time of performance. So we coming to control system. We run on Apex control system. The front end of this control system is called JBlueEyes. The name is due to look and feel of Stanford BlueEyes control system, but it's quite a different system. It has a tab interface. Each tab basically is concentrated on a specific type of the part of the experiment. It's a Java-based graphical user interface, it is a thick Apex client, and the whole architecture is modular and quite loose, which is made intentionally. So what I mean loose in this case is that the JBlueEyes can do some, if you want to do, you can implement some part of the controls in JWS, or you can implement them in a separate server. And JWS depends on multiple servers. These are mostly APEX state notation IOCs, or these are scripts and so on, written in various languages. And depending on your resources in your group, you can implement each part of the controls either in JWS or on a server. And we widely use APEX PVs for messaging between these parts, not only for interfacing the hardware, but also to talking to each part between each other. And the whole system is open source, and it can be downloaded from the link shown down here. As I mentioned, in a couple of years, we installed 2 new detectors, Pilatus 36M and Eiger 16M, and it was really a game change for us because of the much shorter readout time and much higher frame rate. So basically, this increase is almost like 3 orders of magnitude, and you have to accommodate not only the new API of the detectors, but you need to provide much stricter synchronization between the components of your beamline, and you need to handle a higher data rate, larger volumes of data, and so on and so on. This is how we manage this problem in terms of interfacing the detector. When we had MAR detectors, JWS, it's a tab responsible for data collection shown here. Doesn't do the data collection by itself, but it talks to a soft IOC, which we call frame processing engine. And in its turn, that IOC coordinates motion controllers, the delta tau PMAC controller shown here, which controls the goniometer and shutter and MAR detector, and it synchronizes them. So JWS basically said, give me an image from the detector, which we commonly call frame, and FPE controls all this equipment, and basically tells you, okay, the frame is ready, JWS can read it and display it here. It's good, but at hundreds Hertz data collection, it doesn't work anymore, not mentioning that you can do shutterless data collection when you have these fast detectors. So we modified the FPE, created a multi-frame processing engine. The hardware is interfaced more or less similarly here, but JWS now tells I want a series of images. So this all moved to a lower level, and JWS asynchronously watch for the progress. But what should be mentioned is that in both cases, FPE or multi-frame FPE, it basically preloads the motion controller and pre-programs the detectors to the data collection. And then at the end, when the start signal is sent, everything is synchronized and controlled by motion controller in both cases. And the motion controllers, they run internal PID loop at 2 kHz, which is good enough to synchronize 100 Hz data collection. So in terms of algorithms of synchronization, we do what many other beamlines do. We do just a synchronous start. So the detectors start signal to the detector to collect series of images is sent from the motion controller, then controller just records its position. But we found it's more advantageous and more reliable to sync the beginning of each image or each frame from the motion controller, because in this case we can also do frame auditing. It's a mechanical device. You cannot really guarantee with 100% that it will be moving uniformly. We also do crystal searching, which is running the crystal in the X-ray beam from left to right and down, from right to the left and back. And each line here is managed by this multi-frame processing engine. And again, if you do this synchronization for each frame, you can do a single arm detector operation, which reduces time for the pauses between starting each row. And one more thing here. When you run, again, at 100 Hz or even at 10 Hz, you can display images. You can display every 10th image or every 100th image, but human eyes is not good enough for displaying such a fast movie at 100 Hz. So you need some kind of a criteria what's going on with your crystal, whether it's decaying, where it's still shooting your X-rays on a real crystal somewhere else. So we implemented a spot finder, which processes images and calculates number of spots, diffraction spots on the image, so you can at least have some criteria what's going on with your crystal. And this is very important. Extra fun with Eiger detectors. As probably some of you know, with Pilatus detectors, the output format of the detector was CBF, which is common for crystallography, but for Eiger, detectors decided to switch to HDF5, which is very good format, but there are some gotchas. First of all, we use a lot of automated processing software, which was not ready for it. And we use like more than a dozen of different packages. First, they were not ready at all, and everyone started implementing their own converter. You don't want to convert your image 10 times. So we had to do is writing data in HDF5, then converting them for all packages, and then basically run everything from the converter. But this doubles data amount of data you have to store on your disk. Second thing is the way the detector is implemented it. HDF files are first recorded on in the RAM of the black box detector control computer, and until the whole series of images is written, you cannot access them, so you cannot start data processing, which is not really good. That's why what we did, fortunately, there is a second way to interface detectors, is not using the file writer, but they're using the 0MQ stream interface. So we implemented 0MQ reader, which actually reads on the fly buffer through network socket from the 0MQ streamer, and then it can record either CBF or HDF5. For now, we only write CBF5, but we foresee that with time when all the industry, all data processing software adapts to HDF5, we can easily switch. It's just a switch in the software. And this operates very well at least at 100 Hz, which is what we need for now. Automatic data processing. We started automated data processing quite long ago, and it was convenient for users to estimate what they measure. But with switching to new detectors, this really became a must, because data acquisition overruns human brain. If you collect your data set in 10 seconds, or you can do it in 15 seconds, and then scratch your head for 1 hour, this fast detector doesn't help you. You don't need it, basically. So you need to do it on the fly. So you need to start reading your data, processing your data, and get some results at least in 1 or 2 minutes after the data collection is finished. And so we run it on a cluster. We started with several pipelines connecting different data processing software. And just last month, we updated our profile from C# script to Python script, integrating multiple different profiles which users can choose. Our cluster is actually 270 CPU cores dedicated to data processing. And we use grid engine to distribute evenly the processing tasks between different cores. We also tried the Argonne Leadership Computing Facility. You know, Argonne has several supercomputer centers. And we only found that if you move all your data there, you can only gain about 20% compared to our cluster. But remember, you need to move data first, where you're losing time. And second thing, the most critical part is you need to schedule it. The way you need data now, immediately. while supercomputing centers are more oriented towards like scheduled work. You put your task in the queue and wait when it time comes. So it doesn't work fast. We are actually better with our own cluster. But how can we do it? How can we run the supercomputing facility? Oops, I'm sorry. So basically, we upgraded our storage and network. We increased the network speed by 5 times. We increased the storage size by 10 times. And we switched from a shared file system to a distributed file system. This is our topology of our network, which consists of Beamline computers. This is distributed storage. And this is a processing cluster. We just upgraded with 2 more actually computers the previous week, which increased our number of cores by another 100 cores. And we also provide remote access. We do it through a no-machine cluster of 7 computers, so users can log in conveniently through a web browser interface. About 80% of users do it remotely, and it strongly relies on the automounters. So 98% of users use automounters in our case. We just upgraded our automounter. We tripled the number of crystals we can mount contained in the Duo's automounter. It's another Epic server which interfaced from the JBlueIce. JBlueIce just needs to know only 2 commands, mount to unmount. And we also work on the automation. We try to reduce time for Beamline setup. We try to schedule shorter shifts for users because they run out of samples. So what I wanted to tell you, this is my conclusion. Just interfacing these new detectors is not just task of APIs. This was actually the easiest part. It's not the task of not only the task of synchronization. It should be tackled comprehensively from all parts, and you need to revise all parts of your control system. Thank you very much, and thank you, organizers.